Hello, in this video, we'll be discussing operational amplifiers, or as they're usually called, op amps. We'll be discussing what they are, their history, how they are implemented, and their characteristics. And then we'll show how they're both used in ideal versions on circuit simulators, along with models that more approximate the real-world models. Lastly, we'll be discussing their various operations that make them a very versatile active component. Now, what exactly is an op amp? As I've already mentioned, it's short for operational amplifier, and it's an electronic component that amplifies the difference between two voltages. The name's origin actually comes from its original purpose, providing electronic components that could add, subtract, integrate, and differentiate, which allowed for equations to be solved for the first time via early electronic analog computers. While op amps began their life as vacuum tubes, they eventually moved into other implementations, such as integrated circuits, although in this case, vacuum tubes are actually still being produced and used for things such as audio amplification. There are a number of good starting ones, depending on your needs, and ones such as the NE5532, LM34324, and the LM358 are often found in variety packs of integrated circuits that you'll see sold to cheap for hobbyists. Keep in mind, different op amps have different purposes, different specs. You might be able to substitute one for another, but you really need to check the data sheets. A comparator, for example, is a related component who comes from a common lineage from high gain differential amplifiers, and their job is just to compare two voltages. Now, the history of the amp is a lot more recent compared to some of the other components we've talked about. The history of it began in the 1930s as development began on trying to find electronic methods for solving mathematical equations, with scientists such as Carl D. Schwarzschild Jr. being considered the inventor of one of the first true op amps. It could perform addition and subtraction, although it only had a single inverting input. In 1947, Julie Lubra invented the first modern op amp that had a differential input stage along with two inputs, inverting and not inverting. Somewhere between 1952 and 1953, the first commercially available op amp vacuum tube, the Philbrook K2-W, came onto the market. And then in 1961, the GAP-R P45 became one of the first early solid state discrete op amps, although in this case it was mounted on a card. And then 2 years later, in '63, the UA 702 model became the first monolithic op amp IC. And then 2 years after that, the UA 709 came out and it became the first op amp available in a flat package. And then in 1968, the first truly modern op amp, the UA 741, came out. Now, typical op amp operations can be split into open loop or closed loop. Open loop ones, which lack a feedback loop, include comparators, zero crossing detectors, or level or threshold detectors. Closed loop operations include both inverting and non-inverting amplifiers, summing amplifiers, differential amplifiers, integrators, differentiators, active filters, as well as instrumentation amplifiers, although a lot of those use multiple op amps as opposed to one, and then trans impedance amplifiers. All right, there's an important difference we need to mention moving forward, is there's a difference between ideal op amps, models approximating real-world models, and the real-world models themselves. An ideal op amp is incredibly simplified, and you'll often encounter them in simulators, although some simulators do have options for using something a little bit more specific, or in some cases, actually using some pretty detailed models. They have infinite open loop gain, infinite input impedance, and zero output impedance. They also have infinite bandwidth, infinite common mode rejection, as well as zero input offset voltage and zero noise. It'll amplify the difference between the outfits perfectly without noise, drawing more current, losing signal, or limits due to frequency or speed. Interestingly enough, this actually might be fine for some applications, especially low frequency ones, or just as an educational tool. Every circuit has an ideal op amp with a few variables, not many. And then Falstad also has an ideal op amp with, again, a few variables, but it also has some models for the LM741, 74, yeah, that uses dual power supplies, which I'll get into later, and the LM324 for a single supply with a little bit of settings for each as well. Now, I've mentioned that op amps have a number of characteristics that you'll find on a datasheet. Your typical op amp has two inputs and output, VCC or VSS, which is positive voltage, and either VEE, which is negative voltage, or possibly just labeled as ground, especially if it's single supply only. There are implementations that also give you options for choosing single or double supplies, in that something that has support for double supply can always be set to single mode by putting the negative voltage to ground. ICs often have one, two, or even four op amps, and of course there are some variations for specific models as well. The composition of transistors inside the chip can vary. Some use bipolar junction, others use combined MOSFETs, or even some use JFETs. Now, minus is the inverting or negative input, plus is the non-inverting or positive input. Now, open loop gain is the degree of amplification. It usually ranges from 100,000 to a million volts for volts, or V/V. Keep in mind this amplification is also limited by the power supply, so you're not going to get these numbers. But in theory, that's what the gain is. Input impedance, that's measured in ohms. It's difficult, how difficult it is for the input signal to actually enter the op amp, and usually a high one is desirable. That way it blocks out low voltage noise, which could otherwise enter the signal. Output impedance, same idea, also ohms, but in this case, output, you usually want a lower one. We also have the gain bandwidth product, which is a relationship between amplification and its ability to handle different frequencies, usually expressed in hertz all the way up to gigahertz in some cases. A higher gain usually means a low bandwidth, so there's always a trade-off. Offset voltage is a tiny voltage difference between the inputs, which in an ideal op amp would be zero, although it inherent in any real world model, it comes from manufacturing imperfections, and it's usually just micro or millivolts, but that can be problematic in really precise circuits. Input bias current is basically the same thing, but for current, again, just an unintended consequence of manufacturing imperfections, though it can be an issue with high resistance circuits. Common mode rejection ratio, ability to reject signals found in both inputs. Higher rating means it can clean up noise better. Um, Power supply rejection ratio, ability for it to deal with fluctuations within the power supply. Higher ratio means more stability. And as I've mentioned in a couple of things, noise is that's just unintended signals, with usually low noise being desirable for audio applications, but not so low noise might be acceptable for other things. And then we've got the output swing, and that's how much voltage can be output rail to rail. Meaning if it's that it's rail to rail, it can get extremely close to the power supply voltage. If you're only dealing with positive, obviously that's like 0 to whatever voltage, but if you're also dealing with negative, that could be negative whatever voltage to positive whatever voltage. An ideal op amp will just swing rail for rail, minus 15 to plus 15, no problem. Real life, that's going to be lower. And again, if it's advertised as rail to rail, it's going to be a little better. It's probably never going to get exactly to the power supply voltage though, but it's something to keep an eye on. And then we have slew rate, which is basically just the maximum rate of change in voltage or current per time unit. It's really just a descriptor of how well the op amp responds to sudden change. This basically affects how quickly it can handle changes to inputs, and if it exceeds that rate, you risk signal distortion. A high slew rate can be extremely important for power control, operational amplification, and rapid signal, logic signal transitions. Now, I discussed single supply versus double supply. Well, let's talk about that. Single supply means there's just VCC or VSS, positive voltage input. This works well for microcontrollers as negative voltage can damage them. Also, when you're working with 5 or 3.3 volt standards, as well as battery powered circuits, and there's a couple of models. I want to see the LM358 and the 324, probably the most common you'll run into. And then there's double supplies, and they have both the VCC, VSS positive, and they have a VEE negative voltage input. Obviously, if you want to process AC circuits, that is what you need. Audio analog systems, laboratory analog designs, and anytime you need a big, what they call a big swing or big swing around voltage, um, the UA741, the NE5532 are both common models, and there's many others. Now, keep in mind the output of an op amp can exceed its supply voltages, and they're often going to fall short of rail to rail unless the op amp is basically capable of being rail to rail, and even then it won't be to the full. Also, a lot of the time, if you have a double supply one, you can make it single supply by setting the VE to ground, but always consult the data sheets before you do that. Okay, so we're looking at every circuit now, and this is their op amp. It's ideal. There's no positive or negative voltage. Yeah, pretty simple. So basically, you just have an output pin on the right. You have non-inverting input here on the top. You have inverting input on the bottom. And I mean, you can switch it around if you want, since a lot of schematics have the inverting on the top. But that's pretty much it. And you can set the gain. You can also set minimum and maximum output. But yeah, just the three things you can. Okay, I can actually set a label this time. Oh yeah, okay. Wasn't able to do that before. All right, let's take a look at Falstad and what our options are. We actually have a little bit more here. So we've got our ideals. And in this case, we don't even have to flip. We actually have two options. But the idea is the same. You got your output, you've got your inverting inputs, you've got your non-inverting inputs. So that's still pretty simple. And then you've got your reel. You'll notice two more pins. Now, this is where it's a little confusing because the power, the positive voltage is here next to the inverting, and the negative is next to the non-inverting. This took me 3 days to figure out why this was not working. However, there will be schematics that actually switch these, but I think in all the circuit simulators I've seen, including all the Spice ones, that's how it is. So keep that in mind. Um, and then in terms of editing, you've got two different models. You've got a 324, which is good for single, and you've got the, wow, I can't even switch it again. And you've got the 741, which is good for double supply. Now, with the 324, the only thing you can do is switch the inputs. Okay. It's a basic model, but for the 741, you can change the slew rate, you can change the output current, and you can also swap. So there's, in terms of Falstad. Then moving into QSpice, most basic option. Oh, whoops, not path. Yeah. Is this same idea? You've got the positive voltage up here next to the inverting, the negative voltage next to the non-inverting, and output. You've got some characteristics here. Depending on how you use this, you might be able to erase these. But yeah, pretty much that simple with QSpice. Although with QSpice, you can set up sub-circuits, so something closer to an actual IC implementation. Because keep in mind, these op-amp schematics are just that. You're not going to find a triangle shaped thing with 5 different pins like this in the real world. Though I may be wrong, there may be something out there, maybe something with snap circuits or something. I don't know. But yeah, pretty much just set it. But you can also, in this case, you can set up a library file so you can import a Spice model. You can also make an IC symbol that has one or multiple op amps on it too, if you want something a little closer to a real microchip. And then we have gain. Um, that's the measurement of the amplification of the op amp. In an ideal op amp, it can be infinite. But even if it's not infinite, numbers such as 100,000 or a million can be a bit misleading, as the gain is limited by other factors, and that starts with the power supply. I mentioned rail to rail, which is basically short for meeting actual power supply numbers. If it says plus 15, can it actually output 215? In real world models and components, it can never quite reach there. It can get close in some cases. But if something's advertised as rail to rail, that means it'll probably stretch a little bit further than other models. Plus 15 to minus 15 won't quite reach those exact numbers in real life. Might be something as far down as 12 or 13, and in a rail to rail model, it might be 14 or even a little higher, but it'll never quite be 15. If these limits are exceeded, you have a thing called saturation, and the op amp basically stops behaving like it should. Keep in mind that saturation recovery is a factor, and it actually may be relatively slow compared to other operations. So you can be back down below saturation, but the effects can still be felt for a while. I also mentioned a trade-off between gain and bandwidth, where a higher gain means less bandwidth and vice versa. You'll also have an issue with slew rate related to frequency. Higher frequencies can, the slew rate can be, there's greater effects at higher frequencies, so you might need to find a trade-off. Now, keep in mind also that noise and offset voltage get amplified along with the rest of the signal, so this may become more of an issue at higher frequencies. All right, I'm going to sidestep here and mention comparators, which are a closely related component to op amps. Some even regard them as just a category of op amps. Basically, just compares two voltages and indicates if the voltage on the inverting input is greater or lesser than the voltage on the non-inverting input. It usually goes to high if the non-inverting voltage is greater than the inverting voltage, and usually goes low if the non-inverting voltage is less than the inverting voltage. You'll see this a lot with battery checkers, zero crossing detectors, pulse width modulation generation, and analog to digital circuits. Probably the closest you'll actually see to the ideal differential op amps in the real world. The LM393 is probably the most common model you find, but there's plenty of others. There's even ones that are meant for high-speed comparisons, which may be necessary for given applications. Now, I just mentioned ideal differential op amps, and here we are. It measures the difference between plus and minus and outputs no voltage, positive voltage, or negative voltage. In this example, it outputs 0 if equal, plus 15 if positive is higher than negative, or minus 15 if negative is higher than positive. You could use this to check two different analog voltages and see which is greater if they're equal. Keep in mind with a real op amp, you probably won't have zero voltage for equal, or even a situation where two equal voltages are truly equal. Um, so, all right, so we've just talked about comparators, and let's start with EveryCircuit. We've got two different voltage sources set to the inverted and the non-inverted, and we've got an output. Well, the voltages are the same here, so we've got 0 volts. Let's see what happens when we change it. All right, it's immediately gone to negative 15, so rail to rail. So that tells us that the inverting output is greater than the non-inverting output. Let's switch that back, goes to 0. Let's switch it again. Now we've got positive 15. And increasing that number isn't going to matter. At least it shouldn't up to the voltage rails. Now, again, this is basically perfect, so it goes rail to rail. So 20, even then it's not affecting. Let's see, set it to 80. Let's set it to 70. Set it to 70. All right, and we're back to 0, 60. In real life, I believe there's problems once you hit the minimum and maximums there. All right, now looking at Falstad, we've got an ideal op amp right here on the right. And again, the voltage is the same, so the output is 0. Well, let's increase the non-inverting. Okay, it goes positive. Let's decrease it, goes negative. Pretty simple, just like in every circuit. Now over here we have a real model, which I think the fact that it shows both 6 volts in there, it's actually showing a positive voltage here, might be some kind of limitation of the simulator itself. Now in real life, these voltages would not be perfectly equal, so getting 0 volts out of here um, would be a little fussy, but you'll notice when we change it, it goes up, it goes negative. So when the inverting is higher than the non-inverting, it'll go to a negative value. We switch the other, it's the same, it goes down. It's still a comparator, but again, I think this is a problem with the simulation. And we have two models, which will change the numbers somewhat. So this is a single, doing that, so it goes to negative 15. And then the double supply is actually going to a different number altogether. But again, I think this is a function, a limitation of the simulator itself. Okay, now we're looking at QSpice with a comparator. Ignore the fact that everything's spread out. The labels connect everything. But yeah, we're starting out with 5 volts on each, and we're going to run it for 5 milliseconds. Let's see what kind of results we get. All right, as you can see in the plot here, we got 5 volts on inverting, 5 volts on non-inverting. This is 0 volts, whatever, but basically it's 0. So let's move some values around here and see what we get. So let's boost the inverting to 6, see what happens. All right, now looking at our plot here, we've got 5 and 6, and now we've got negative 15, which is what we should be looking at. Now let's change voltage in the other direction, or actually let's boost this up to 10 and see if that makes a difference. All right, it actually doesn't make a difference. We still got the same negative 15. All right, let's flip it the other direction. Let's run that. All right, let's get those numbers. Now we have a plus 15, just like we should. All right, so what else is there? Well, the ideal differential op amp we just looked at is basically just a voltage comparator and open loop, but most operations require a closed or feedback loop, and they often require external components such as resistors and capacitors. Now, open loop gain is the gain where, as you guessed it, it's an open loop, but that gain can be really unpredictable. The next topic, of course, we need to cover is the feedback loop and how to manipulate it, usually with resistors, to get the gain. That's the basis for using the op amp for other operations. Now, a feedback loop is just when the output is fed back around to either inputs. Forces the output to stay in equilibrium with that connected input. You can also use a pair of resistors, often called the input and feedback resistors, to set that gain. Now, what is a closed loop circuit as opposed to an open loop one? And what is feedback loop? Well, it's when output is fed about around back to either the inverting or non-inverting input, often coupled with either resistors or capacitors to set the gain. When you connect the inverting input to the output, you get a negative feedback loop. The output tries to stay in equilibrium with the inverted input by reducing the output voltage. That can be useful for stable gain and increased bandwidth, but also reducing distortion, noise. It can even improve input or output impedance. Some of its uses, phone, headphone jacks, audio amplifiers, voltage follower buffers for sensors, summing amplifiers for audio mixers, even car cruise control, believe it or not, and even power supply voltage regulation. On the other hand, we have positive feedback loops, which cause the amplifier to saturate, sending it rail to rail, an instant snap to one extreme or the other, well, at least as far as the model allows. And of course, positive feedback is when we feed it back around between the non-inverting and the output. Where this is useful is for switching hard between states, reinforcing changes, creating hysteresis, which we'll discuss in later videos, Schmidt trigger input circuits, again, something we'll discuss in later videos, 555 timer oscillators, which again will probably have its own video, flip-flops, and by extension, computer memory. And as I said, and as you guessed it here, topics all covered in later videos. Now, the first type of operation we're going to discuss is the unity gain buffer. It's actually known by a number of other names: unity gain amplifier, just a gain follower, a voltage follower, or even just follower. It starts with a negative feedback loop that we previously discussed, but we're not using any resistors or capacitors in this example. We've added a 5-volt DC power source to the non-inverting input. There's no gain whatsoever, and actually that's the point. It can act as a middleman buffer in a circuit that isolates it, and with some other components, it can actually get rid of noise and bring the signal up to the correct value for the rest of the circuit that it's in. The high input impedance draws almost no current from the source, and the low output impedance means it can drive much heavier loads with ease. Now, starting out in every circuit here, I've made a unity gain buffer. In this case, I've made it a sine wave amplitude of 5 volts, 40 hertz, and that is in the middle here. And then the feedback loop here is pardon me, orange. Unfortunately, I'm colorblind, so I can't see between the two colors. But there's no way to change it in every circuit. But the output is the blue here, and you should be able to notice everything's exactly the same. In fact, I can actually look at the numbers right here. It's all the same, and that's the point. Now moving on to Falstad, basically the same idea here. Hertz is a little bit different, but 5 volts, 60 hertz. On the left, we have the source. On the right, we have the output. Basically the exact same numbers. Though I'm using an actual model, using a 741 here. So there is a tiny bit of difference. This is actually a model, but it's basically insignificant for this purpose unless we were being really, really precise. So it's 5.001, and I really don't know how much of that is the model in the actual simulator. In this case, we've got our positive. Actually, this is, oh, no, no, okay. On the bottom, we have our negative 15 volts. I've just got the terminal switched around. And on the top, we've got our positive 15 volts. So rail to rail, it'll go 15. What it can actually go to, I'm not entirely sure off the top of my head. But that's why we got it 5 volts. We're keeping it really low. But yeah, it pretty much just follows the same thing, and that's the whole point of it. Now, finally, all right, now we're taking a look at the Unity gain buffer in QSpice. Pretty simple setup here. So we've got our positive and negative rails. We've got our output. We've got a simple input, which is a sine wave of amplitude of 5 volts. So it's going to go 5 to negative 5, working at a pretty slow 40 hertz. So as you can see from the plot here, we've got our in and we've got our out. Exact same amplitude, everything. So unity gain buffer. All right, we're going to move on to the inverting amplifier. In this case, the output signal is amplified and is flipped upside down. The signal is shifted 180 degrees. This uses a negative feedback loop by connecting the inverting input through a resistor to output. The non-inverting input, on the other hand, is simply tied to ground. There's also a feedback resistor between the inverting input and the output, so we're dealing with two resistors now. The gain itself is determined by a ratio between the two resistors, and the actual value of the resistors affects the amount of current. Keep in mind the gain is still restrained by, among other factors, the power supply. Remember to keep that in mind because real life models aren't always perfect rail to rail, although they can get pretty close. Now here we're looking in every circuit at an inverting amplifier. I've also added a third resistor and an LED because pretty big blinking lights. You'll notice that the positive terminal, that's the non-inverting input, has been tied to ground. We've got a sine wave here doing an amplitude of 5 volts at a frequency of 1 hertz, so it's nice and slow. Um, so going through a 200 ohm resistor and then a 400 ohm resistor, this means that we're getting a gain of 2. The output signal is both 100 degrees, 180 degrees out of phase, and twice the signal here. As you'll notice, our bluish color here is the original signal, and the green is the output. All right, we have another example here in Falstad. This is part of the examples that comes with the program. We've got a 40 hertz, 5 amplitude sine wave that's on the left here. We have a 1K resistor and a 3K resistor. So we're actually getting a gain factor of 3 here. So 5 volts is becoming almost 15 volts. In this case, we're using a ideal circuit, so no power supply pins. All right, here we've got an inverting amplifier set up. You see our power rails, 15 and negative 15. You see our negative feedback loop going through a 1K resistor back into the inverting input. Then you see another 1K between the inverting input and our voltage in power source, which is a sine wave going from negative 5 to 5 at only 2 hertz. Now, taking a look here at the waveform, we see our original in the green color, and then we see our output in the blue. And yes, you'll notice same amplitude, but 180 degrees phase shift. Now we're moving on to the non-inverting amplifier. In this case, the output is still being amplified, but there's no phase shift. This was actually accidentally discovered by scientists at some point, since correcting for phase shift with an inverting amplifier can be a pain, especially when it's not what you want to do. This time, though, the input signal goes into the non-inverted input, but there's no resistor. We still have our feedback resistor between the inverting input and output, and as I mentioned, this is still using a negative feedback loop. Our second resistor, on the other hand, is between the inverting input and ground. This is sometimes called R1, R2, Rn, some other labels. Usually the feedback resistor is RF. The ratio also has a new interesting effect that can affect how sinusoidal or square the output actually is. This lets us create a Schmidt trigger, which, as I said earlier, is something we'll cover in a later video. The relationship between the resistors divide voltage, but you can make that division so small that you can basically turn the output into a voltage follower. An example of this is setting the feedback loop resistor to 1 ohm and the other resistor to 100 ohms. Keep in mind that the values of the resistors, as always, still control the overall voltage, the overall current. Keep that in mind when you're adjusting resistor values, especially in real life. All right, let's start over in EveryCircuit, taking a look at a non-inverting amplifier. You'll see the placement of the resistors. I got one at 100, one at 200. What is this actually doing? In this case, our blue is 5, so we've actually got a gain factor of 3. And you'll notice they're not phase shifted at this point. That's pretty powerful. Question is, what do we do when we check these values? Let's put the other resistor to 1. Oh, there we go. You'll notice square pulses here, which are affected by the input. It goes up, it rises, it goes down, it falls. This is going to be a very useful concept later on in later videos. All right, let's put it both to 200. What happens? Okay, we've got a gain factor of 2 in this case. All right, let's look at Falstad here. We've got a non-inverting input here. You'll notice we've still got we got this gain factor of 3, similar to the other thing we looked at. We're just moving faster at 40 hertz. And yeah, we're at a max voltage of 5. Again, this is an ideal op amp. So yeah, you'll notice gain factor added. Even though they're not overlaid, let me assure you that they are not phase shifted. But let's change some numbers on this one. Get 100, 1 set. Let's see what we get. Yeah, see, that's just changing. That's making it a follow, essentially a follower, more or less. Let's change these values around again. All right, and look at this. We've got the same idea that we showed in EveryCircuit. Now we're looking at a non-inverting amplifier in QSpice. We've got our power rails in this case. We're going with 15 and negative 15. We're looking at resistors of 2K and 4K. Now notice the placement here. Power source in is a sine wave 5 volts, so 5 to negative 5 and 40 hertz. All right, we're going to take a look at the waveform here. Our original signal is the green, our output is the blue, and you'll notice it's a gain factor of 3, but it is in the same phase. So let's mess around with the values here. Let's make this 4K and 4K. All right, we're looking at a gain factor of 2 in this case. So 5 volts goes up to 10 volts, obviously still stays in the same phase. All right, we're going to make some adjustments here. We're now doing 100 ohms at resistor 2, and we're doing 1 ohms on the feedback resistor. All right, we've created a voltage follower here, as you notice, same phase, basically the same amplitude. All right, let's flip those values around and see what we get. All right, and this is where we see pulses coming out of the output, even though we put in a sine wave. And at least here we've got an interesting effect, as it were, in terms of the gain factor. We're looking at what, 5 volts to 14. All right, next we have the summing amplifier, which sums up multiple input voltages all tied to the same input into a single output. It also might be better understood as a weighted sum voltage adder. The more common variant is the inverting summing amplifier, where the input is on the inverting input and the non-inverting input is simply tied to ground. Each individual input voltage gets its own resistor, which weighs the inputs, where a 1-to-1, as many inputs as you actually have, gives them all equal weight. The result will be negative since the output is 180 degrees out of phase. The non-inverting variant can work a bit differently in that it averages the values and then amplifies the result, with the result being in the same phase with a positive output value. All right, let's start with EveryCircuit here. So this is a inverting summing amplifier. I've set all the resistors to basically the same here, so that keeps it simple. So basically we've got, let's see, 2 volts at 1 kilohertz, 5 volts at 1 kilohertz, and 1 volt at 1 kilohertz. And our output is giving us 8 volts. You'll also notice that the inputs versus the outputs, they're 180 degrees out of phase. Now here we're looking at a non-inverted summing amplifier. We're only dealing with 2 values right here, but yeah, we've got 2 volts at 1 kilohertz. We've got 3 volts at 1 kilohertz. And surprise, surprise, we're getting a total of 5 volts at 1 kilohertz. And keep in mind, everything's in phase with non-inverting. Now let's take a look at Falstad. We're starting with a inverting summing amplifier. We've got 200 hertz at 5 volts. We've got a 20 hertz pulse at 2 volts, which has given us 7 volts. Notice the mixture of the waveforms here and the output. Now we're looking at a somewhat different setup with the non-inverting. Um, so everything's within phase now, and that could have an. And of course, we've got the 100 hertz 5 volt sine wave here. We've got 20 hertz pulse wave at 4 volts. We've got the 9 volts, and we've got the combined waveform on the output. All right, we're moving over to QSpice now for an inverting summing amplifier. This is actually based on a model, the LM324, although it doesn't completely function as real life because, as you can see, I had a negative power source connected to its VCC negative. Now, I believe in real life that would probably fry the chip. But this is how we would actually configure it in real life with a ground to VCC negative. We've got inputs of a sine wave, amplitude of 5 uh, volts and 20 hertz, and then we've got another sine wave, an amplitude of 2 and 50 hertz. So we've got both different voltages and different frequencies. So let's take a look at how this runs. All right, so let's take a look at our waveform here. We've got a 2 volts here. We've got the 5 volts here, obviously different frequencies. So we're going to get different answers. Now, the fact that we're using an LM324 means we're not going to get negative part of that waveform, but for our purposes, that's fine. 2 plus 5 equals 7. And obviously, we've got this kind of weird waveform because we're dealing with different frequencies and different voltages. All right, now we're looking at a non-inverting summing amplifier. You'll notice things are hooked up a little bit differently. So we've got our positive power rail, and since we're doing this with a LM324 model, we've got ground on the negative. And our inputs are a sine wave, 2 volts, 20 hertz, 3 volts, 40 hertz. And we've got our output. So let's look at how this works and what it gives us. All right, I've made a little bit of a change to the circuit. So we're doing both 40 hertz on each sine wave. So let's take a look at what that looks like. All right, so one input is 2 volts, 2 to negative, one is 3, 3 to negative, and our output is just 5 volts because again, we're dealing with single supply LM324. Now we come to differential amplifiers, and that's basically an op-amp circuit that amplifies the difference between two input voltages by also rejecting voltage common to the two. Now you'll remember that we already mentioned differential amplifiers earlier in the video. It's important to note that this is restricted to two inputs, although you can use multiple stages for more than two inputs, but it turns it into a complex circuit instead of a simple one. You want to balance the input resistors. You want to make them the same value, or it basically breaks the purpose of this amplifier. It doesn't have quite the same value as weighting with the summing amplifier. It might have some use as a general linear analog weighting network, which is really just a fancier way of describing a weighted operation. The feedback resistor still sets the gain, or in this case, how strongly it amplifies the difference. This works well enough for voltage subtraction, but its real power actually is in it detects the differences in signals and outputs the difference, which is great if those signals are supposed to be otherwise the same. You might use it to compare two different audio signals, which should otherwise be the same. We mentioned how a comparator is basically just a high gain differential amplifier, although we often still describe a comparator as its own component, as ICs for comparators are very specific to being comparators. The high gain is ideally rail to rail, and that's why they're often different ICs. All right, we're going to start in EveryCircuit here, and this is a basic differential amplifier here. We're taking the number connected to the non-inverting input and subtracting the number on the inverting input to it. So we've got 10 volts DC, we've got 2.5 volts here, and then we're outputting 7.5 volts. Again, we're just working with DC here to keep it simple, but actually let's, you know what, let's change it to a sine wave. Let's make it 10 volts. Let's do the other sine wave to 2.5. Where's our number, I believe? Oh, whoops, didn't take. No, this is the problem with EveryCircuit. All right, so let's actually just reset it. But yet 10 minus 2.5 is giving us 7.5, and there's no kind of phase shift here. All right, let's look at Falstad with a differential amplifier here. We have 6 volts DC going into the non-inverting, and we have 5 volts DC going into the inverting. And we're outputting 999.98 millivolts, 8 kilovolts, but basically 1. We're subtracting 6 from 5. So let's play around with this. All right, let's set this to a sine wave. Set this to a sine wave as well. Same frequencies. Let's reset. So there we go. It's in phase. And we're seeing the difference is the basically 1 volt over here. Well, let's see what happens. Mix those frequencies. This actually changes it quite a bit. But it's still giving the difference. It's not doing the subtraction anymore, but again, it's still showing us the difference. So it's no longer good for voltage subtraction, but it is good for showing the difference of the signals. All right, let's take a look in QSpice here. We've got 5 minus 2, and obviously this should give us 3. And yeah, it basically does. I mean, there's a little bit of a difference here, but that's just the model. All right, let's play around with some of this. Let's make this a sine wave. I don't know, frequency 20, I don't know, whichever. All right, let's see what the numbers look like here. All right, as you can see, pretty much the same idea. We got our plus going up to 5, we got our minus going up to 2, we subtract the 2, and it goes up to 3. All right, let's change the frequency here. All right, we've changed our frequency, or won't change our frequency, I should say. Set one to 40 and the other to 20. Let's take a look. All right, let's look at our waveform here. We got our plus, got our minus, 5, 2, and it does something different. We no longer can use this as a voltage subtractor, but it does show us the difference between the two. Said it does show us the difference between the two. It just the voltage numbers don't line up anymore. But this is the key of a differential amplifier. All right, just to wrap things up, I'll be covering some more on op amp circuits and types in a future video. Keep in mind, as I said, an op amp just amplifies difference between two voltages. It got its name from the original intended purpose, basically electronic method for mathematical operations. It did start out as a vacuum tube, like a lot of components, and the earliest ones could really only handle basic addition and subtraction. They eventually migrated to solid state discrete forms and eventually to ICs in the 1960s. There's many different types of operations: inverting, non-inverting, summing, differentiation, transimpedance, and instrumentation, among many others. A comparator just compares two voltages, giving rail-to-rail answers, or as far as the IC can give you, essentially just a high-gain differential amplifier. You're just comparing values and trying to figure out which is bigger than the other. You don't really care about gain. We talked about open gain loops versus closed feedback loops, where the amount of gain actually matters. We also mentioned that the feedback loop could be negative or positive. Inverting it, an inverting amplifier puts the output signal 180 degrees out of phase, while the non-inverting just keeps it in phase. First, we after comparators, we mentioned unity gain buffers. They're known by a lot of different names. And it doesn't apply any gain or change to the signal. It just passes it along from input to output. Um, we use a feedback resistor to actually set the gain with those amplifiers. We showed addition with summing amplifiers. We showed subtraction and differentiation with differentiation amplifiers. Well, until next time, have a good one.